Okay, welcome back. So we are continuing with the Higgs boson saga, and you may be wondering now, we should have probably just skipped the Higgs boson. But I really hope that the information that we are finding out about how intricate the universe is as fascinating to you as it is to me, because this has taken us on a wonderful journey through symmetry, through the standard model, through this delicate idea known as gauge symmetry, and so on. Okay, so to start us off here, let us think about something we're very familiar with, which is the revolution of the Earth. We know that the Earth spins on its axis once every 24 hours, but what we may not have thought about is what is known in the lingo of physics as the parity of the spin, or the handedness of the spin. The Earth spins counterclockwise when looked at from the North Pole. And it is this counterclockwise spin that brings the east first in the direction of the sun and then the west. So the sun rises in the east and sets in the west, and why, for example, New York is 3 hours ahead of Los Angeles. So this is also sometimes known as uh, depending on how you want to label things, a left-handed spin or a right-handed spin. But for now, we will just talk about a counterclockwise spin to the Earth as viewed from the North Pole. Now, this is not a necessary thing. It just happens that the Earth is spinning in this way. Most of the planets in our solar system, in fact, spin this way in a counterclockwise fashion. But Venus, for example, has a retrograde spin. It spins clockwise when viewed from its north pole rather than counterclockwise. And so, very interestingly, on Venus, the sun rises in the west and sets in the east. Now, before we go on to talk about the physics, I have to note that this immediately recalls to my mind a nice verse in the Quran when Prophet Ibrahim alayhi salam was having a discourse with the king who thought that because of his kingship he was all powerful. And this is verse 258 from Surah Al-Baqarah. I won't go through the whole verse, but Prophet Ibrahim, peace be upon him, was telling the king that it is God who gives life and who gives death. And the king said, well, I give life and I give death. And so Prophet Ibrahim told him, فإن الله يأتي بالشمس من المشرق فأت بها من المغرب فبهت الذي كفر والله لا يهدي القوم الظالمين. And so Prophet Ibrahim replies to him, verily God causes the sun to rise in the east, cause it then to rise in the west. Thereupon he who was bent on denying the truth, that's the king, remained dumbfounded, for God does not guide people who deliberately do wrong. And so this notion of the sun rising in the east is because the earth spins counterclockwise. It does not have to be that way. It could have been like Venus and spun clockwise. And so what Prophet Ibrahim was in effect telling the king is that it is God who has made the earth spin counterclockwise. If you think you are so powerful, go ahead and make it spin clockwise. The idea here, though, for our purposes, I just couldn't pass up this Quranic connection, but the idea for our purposes is the notion that spins can be clockwise or counterclockwise. In physics, it's more often discussed in terms of left-handed spin and right-handed spin. So it turns out that when we look at elementary particles, and this is only a very rough analogy, but elementary particles like electrons, like neutrinos, and so forth, have spin. And they can spin in either a right-handed way or a left-handed way. Here is what is known as a right-handed spin. And the way we get this convention is that you take your hand and you curl your fingers along the direction in which the particle is spinning, and you see where your thumb points. So if you were to take your right hand and curl it in the direction of this spinning arrow, your thumb will point up. And because it points up along the direction of this arrow, we say that this particle here has right-handed spin. If you were to try to take your right hand now and curl your fingers in this direction, in the direction of this spin, your thumb would point down. The only way you could have your thumb point up is if you were to take your left hand and curl the fingers in the direction of this spin. And so this is what is known as a left-handed spin. And so electrons, neutrinos, quarks, etc., all have spin, and that spin can be right-handed or left-handed. And if you were to put a mirror, a left-handed spin reflected in a mirror would look like a right-handed spin. So this is known as parity. And so the question becomes, do the laws of physics have symmetry with respect to a parity transformation? Will they treat a left-handed spinning particle the same as a right-handed spinning particle? And so, for example, early versions of the Standard Model, early investigations thought, of course, because we want to have parity symmetry. And it turned out that the laws of electromagnetism treat right-handed and left-handed electrons exactly the same. The laws of gravitation work exactly the same. So that's why Venus is attracted to the sun, if you will, by the same equations of gravity that the Earth is. We can use Newtonian physics to calculate the orbit of Venus, just like we can use it to calculate the orbit of the Earth, even though their spin parities are opposite. So electromagnetism shows parity symmetry. A parity transformation does not affect the equations of electromagnetism. Gravity shows parity symmetry, and we thought that that would be the way it is with all of the forces of nature. So two scientists named Li and Yang notice that, well, we are just assuming that the weak nuclear force, the strong nuclear force, will also show parity symmetry, but that it hasn't been checked for the weak nuclear force. And the weak nuclear force is the force involved in particle decay, when one particle changes into another. And they hypothesized that the weak nuclear force may not show parity symmetry, may not show parity invariance. It doesn't have to treat left-handed and right-handed particles the same. And then this was actually demonstrated by a very colorful character in physics known as Madame Wu in the late 1950s. And Li and Yang won the Nobel Prize in 1957. Why Madame Wu was left off, I don't know. But, for example, a positive pion, when it decays, if there was parity symmetry, one of its decay products is a neutrino. A pion is a subatomic particle. And when it decays, one of its decay products is a neutrino. And if there is parity symmetry, there would be an equal amount of left-handed and right-handed neutrinos produced by the decay of positive pions. Why? Because here you're looking at a left-handed neutrino, and if we were to reflect in a mirror, that would look like a right-handed spin neutrino. So if there's parity symmetry, us and our mirror world would look the same, would be the same. But it turns out that in our world, we only see left-handed neutrinos. No right-handed neutrinos are ever produced by the decay of positive pions, positively charged pions. And so this showed that the weak interaction does not respect parity symmetry. Parity symmetry is violated. Who cares? Well, soon you will see now how significant this is. Why is all of this significant? Finally, we get to the close to the end of our journey, understanding what any of this has to do with Higgs bosons. So bosons, like the W bosons, are spin 1 particles. And we've already talked about how scientists had decided that gauge theories or gauge symmetry must be at the heart of the standard model. But when you attempt to write the Lagrangian for spin 1 particles using gauge theory, the theory gauge symmetry requires that they have 0 mass. And we already know that W and Z particles do not have 0 mass. In fact, they're 80 to 90 times as massive as a proton. Also, separately and also, parity violation requires that the weak force treats the right and left-handed particles differently, like we just saw. Now, the only way to include mass terms in the Lagrangian when we're writing a gauge symmetry for the weak force is to have equal treatment of the right-handed and left-handed states. So a mass term in the Lagrangian would be inconsistent with an asymmetry between right and left-handed states. But this asymmetry obviously exists in nature, as we just saw. And so the standard model would predict that quarks and leptons, like for example the neutrinos we were just talking about, or electrons, as Madame Wu demonstrated, parity violation with electrons for weak force decays, it would predict that they would have to have no mass if we wanted to stay consistent with gauge symmetry. So on the one hand, we really want a universe, laws of physics, that are ruled by gauge theory that show gauge invariance. On the other hand, a gauge theory would predict that things like W bosons be massless, and separately, for different reasons, if there is parity violation, it would predict that the particles involved, like electrons and neutrinos, would also be massless. So now we're stuck. And what was the way out? The way out was in the 1960s. Peter Higgs and others proposed that the way out of this is to hypothesize a new and different field, in addition to the electron fields and the quark fields and the gauge fields that gave us the bosons and so forth. And this field came to be known as the Higgs field. And what the Higgs field does as a gauge field is it can interact with these other particles to maintain gauge symmetry, but to fix these problems. And understanding how that works would require near a PhD in particle physics, but this is now what any of this has to do with the Higgs field. We had to take the journey to understand gauge symmetry, to understand left-handed particles, to understand right-handed particles, and now we understand the conflict that in the original formulations of the standard model, gauge theory would have predicted that spin 1 particles like W bosons have 0 mass, and either parity would not be violated, or if there's a parity violation, the particles involved in parity violation would also have to have 0 mass. But this contradicts empirical evidence. These two statements are not true, and so either we have to throw gauge theory out the window or introduce a new gauge field, the Higgs field, that can maintain gauge symmetry but fix these problems. And that is exactly what the Higgs field does. And the manifestation of the Higgs field is the Higgs boson. And that is why there was a 50-year quest to find the Higgs boson. Because if the Higgs boson were not to be found, the entire structure that had been built would have come collapsing down. Okay, so now we understand why the Higgs field and the Higgs boson are so important and so central to the Standard Model, and why the most expensive scientific instrument in human history was built to try to find it. Because it is at the heart of our understanding of what is behind the curtain of everyday life, of the macroscopic world that, of cars and people and baseballs is made up of these subatomic particles. And uh, the Standard Model is central to understanding their interactions, and the Higgs boson is central to the Standard Model. Before we go on, I want to just throw one more term at you. And if we look here at the bosons, we said that they are called gauge bosons because they are the result of gauge fields. They are the manifestation of different gauge fields. And each of them is described by gauge theory. And we talked about how there are different gauge theories that have to do with so-called different symmetry groups in mathematics. What I want to call your attention to here, though, is that the force carrier for the strong force is massless. The force carrier for the electromagnetic force, which is the photon, is massless. But the force carriers for the weak nuclear force have significant mass. Again, something in the range of 80 giga-electron volts and 91 giga-electron volts, so 80 to 90 times as massive as a proton. Now, a Nobel Prize some years ago was awarded for the discovery that at the dawn of the universe, the electromagnetic force and the weak force were actually a single force. They were identical to each other because of an underlying gauge symmetry that united them. And then, very early in the life of the universe, they sort of came to a fork in the road, and the weak force branched off on its own, and the electromagnetic force branched off on its own. But at heart, they are a single so-called electroweak force. And so scientists talk about how the symmetry between these two forces was broken, and this has no mass, and these have mass. And this concept of symmetry breaking was also central to the need for the Higgs field, because without the Higgs field, this symmetry breaking could not be explained. So that is yet another reason why the Higgs field sort of had to be hypothesized, had to exist. We've talked about it had to exist to give particles like the electron and the quark's mass, and the W and Z bosons mass. And part of giving the W and Z bosons mass was this process of symmetry breaking between the electromagnetic force and the weak nuclear force. So I just want to show you something from a website here that talks about, again, Higgs boson physics. Again, to hammer home the point that two of the most intriguing mysteries of nature are electroweak symmetry breaking. Why did the electromagnetic force and the weak nuclear force break apart? And the origin of fundamental particle mass. So electroweak symmetry breaking and the origin of fundamental particle mass. And in the Standard Model, the weak and electromagnetic forces have the same strength at very high energy, such as existed in the very early universe, described by a single electroweak interaction, and particles must be massless. So these two things had to exist to preserve gauge invariance. And again, gauge invariance is that the thing that in which different configurations of the fields lead to identical physical results. And again, gauge invariance is a required ingredient of any quantum field theory describing nature. And we now see that electroweak symmetry is broken. They are not any longer the same force. And we also know that the W and Z particles do have mass. They are not massless. And so how to solve these problems while maintaining gauge symmetry? Well, that is where the Higgs boson came in. And again, you can read this on your own. I don't want to just be sitting here reading things to you, but basically particle masses arise when the electroweak symmetry is spontaneously broken by the interaction of massless fields with the Higgs field, an invisible spinless field that permeates all space and has a non-zero value everywhere. And these are just technicalities of the field. And if the standard model description of electroweak symmetry breaking is correct, then a single massive neutral spinless particle called the Higgs boson must exist. And so the Higgs boson was hypothesized theoretically to maintain gauge invariance, but to solve the problems that gauge invariance would otherwise pose, such as that the W and the Z particles have mass, but that the photon is massless, that we have this symmetry breaking between the electromagnetic force, where the photon is the force carrier, and the Z and W bosons that carry the electroweak force, and to also give things like the electron and the quark masses as well. And so you see here, before July 4th, 2012, the Higgs particle had never been observed, and then it was found in proton smashing experiments at the Large Hadron Collider. Okay, I just want to very briefly show you this diagram because this is sort of the standard diagram of the shape of the Higgs field and how the Higgs field breaks symmetry, how it causes so-called spontaneous symmetry breaking. If the Higgs boson is up here in what they call this Mexican hat configuration of the field, that's what you'll read it as in textbooks, the situation is totally symmetric. It can roll down anywhere. Once it has rolled down somewhere, now that symmetry is broken. And so the analogy that I read in one book is if you have a donkey between two buckets and he's thirsty and he is right in the middle between the two buckets, that is a totally symmetric situation. Once he chooses one bucket to go to and drink, that symmetry is broken, but underneath it, there was a sort of hidden symmetry in that he used to be between the two buckets. And so it's a very crude analogy to how the Higgs boson breaks the symmetry between the electromagnetic force, where you see that the mass of the photon is zero, and the weak nuclear force, where you see that the mass of the W and the Z particles is not zero. And again, this is not something we're going to understand immediately. I just want to kind of give you some of the jargon that is used in the field. And so this is another analogy. If you have a vase like this, it has complete rotational symmetry. If you turn the vase by any number of degrees, it will look exactly the same. It is invariant under rotation. But once you paint a picture like this on the vase, now if you turn the vase a little bit, that symmetry is broken. It no longer looks the same if you were to turn it by 30 degrees or 80 degrees or 90 degrees, right? Imagine taking this and turning it by 45 degrees. It would no longer look the same as what you're looking at now. So there's an underlying symmetry in that before the vase was painted, it was totally symmetric, but once we paint on it, the symmetry is broken. And so that's basically what the Higgs field does. It paints on the rest of the standard model, the masses of the fundamental particles. And it is only the fundamental particles that interact with the Higgs field that have mass. So here's the Higgs boson, and you see that there's an interaction with the leptons, like with the electron, and that's why the electron has mass. It interacts with the W and the Z particles, and it interacts with the quarks, and that's why they have mass. But you notice the Higgs boson or the Higgs field also interacts with itself, and that's why it has mass. but it does not interact with the photon and does not interact with the gluon, and that is why they have no mass. And so it is the Higgs field that confers the mass to the fundamental particles. And once again, if I haven't been able to convince you that that is a big deal, if the Higgs field were to now disappear from the universe, electrons, for example, would have no mass. And you know that all of chemistry, all of the bonding of atoms in our body, one atom bonded to another atom to make us, would end because the electrons would be massless. They would be like a photon and would just fly away. And so the Higgs boson isn't just central to the standard model of particle physics, which you may or may not care about, but without the Higgs field and the Higgs boson, there would be no chemistry, no life. So I know this was long and it was hard, and you may think, gosh, this was tedious. I hope you don't think so. I hope you enjoyed getting a glimpse of the things we kind of take for granted, but these are the big realities, and we're kind of like the the shadow of that reality on the wall. But this is the bedrock of how things are in the universe. So now we understand, in some sense, what the Higgs boson is and why it is important. And then in our next, and I would guess probably final episode in this subseries, we now need to understand, okay, now that we sort of have a feel for the Higgs boson, how is it fine-tuned? Okay, because we haven't talked about fine-tuning of the Higgs boson, but before we could talk about fine-tuning of the Higgs boson, we needed to understand the Higgs boson, because most of us at least have some mental picture of an electron. If I say an electron, each of us imagines something. But if I just say a Higgs boson, probably most of us, unless we have a particular interest in physics, would have had no idea what in the world is a Higgs boson and probably didn't appreciate how important it is. So I hope that you still have a little stamina left in you and that you will tune in with us now to see why the Higgs boson or how the Higgs boson is fine-tuned, because it turns out that the Higgs boson needed to be exactly what it is, essentially, and then that will conclude. So hope to see you then. Take care and God bless.